So today's instructional objective, students will be able to describe how chemical and physical weathering differ. Do now says type your name the four methods of mechanical, physical weathering, name three methods of chemical weathering, and which of these is partially anthropogenic, meaning which of these are caused by humans. Today's mini lesson, we're going to examine some cemetery rocks, and then you have an assignment on Nuzella, an article on erosion, and then you have a separate question you need to answer in the Google Classroom. So far, I only had 3 people respond to this, and I have 7 people in the pair deck. So please get on board. All right, let's take a look at some of the responses. Frost wedging, temperature change, salt wedging, and abrasion. So we got frost wedging is one. Uh, we have root wedging is another. Abrasion is another. Temperature change can lead to thermal expansion, which can lead to exfoliation. We got some good ones on here. Abrasion, frost action, plant action, abrasion, exfoliation. Good. Yeah, so those are the primary physicals. And let's take a look at the chemical action. Sure, Rihanna, here's the link. So the chemical actions are oxidation, carbonic acid, which is acid rain. Cool. Then we have acidification. Acidification doesn't have to be through acid rain. I will talk more about that in a moment. All right. Don't want to cut anybody off, but we do have to move forward. So welcome to Huntington Cemetery. Step inside into another real-life weathering laboratory. So we're going to take a look at some rocks that we could find right here in the cemetery. So this cemetery, Huntington's first public burial place, was opened in 1700. Now, 1909 is when this plaque was put in. You'll notice it's a copper plaque, but it doesn't look brown anymore. It's green. So what you're actually looking at is copper oxides. So we're looking at acid rain, the effects of acid rain on copper. Wow, we haven't even stepped inside and we have evidence of weathering at the gate. What process is this, and is it physical or chemical? Drop your answers in now. All right, beautiful. Pretty much everybody, well, everybody did. Well, almost everybody put down chemical. Yeah, so chemical action in this case on this iron gate or steel gate is going to be rust. So we're going to look at cemetery rocks, tombstones, and we're going to observe the weathering that has occurred in them. Since tombstones are dated, we can even determine how long the weathering has been occurring. Here is a typical marble tombstone, which used to be a very popular rock for cemeteries. What mineral largely composes marble? Now, if you didn't memorize this one, that's okay. Earth Science Reference Table, page 7 is there to help. 2, 1. Calcite, beautiful. Yeah, so let's take a look. If you didn't know how to do that, we're going to go to the Earth Science Reference Table, and we're going to go to page 7. So on 7 on the ESRT, you'll notice here we have marble. Marble is metamorphism of limestone or dolostone, and it's made up of calcite or dolomite. Now, calcite, if we go down here, and the same thing with dolomite, bubbles with acid. So it's probably just easiest to just flat out memorize this one. Calcite bubbles with acid. So what is the hardest of the mineral? You don't have to answer this one on the screen. The answer's not coming up right. But what is the hardest of the minerals? So the mineral is the hardest of 4. And why is it a good rock for tombstones? Well, it's cheap. I guess that's a thing. It's hard enough. You can carve it pretty easily. It's not a very good rock for a tombstone, to be honest. Here's another one. This one's made up of slate. It's a lot easier to read, right? There's definitely a lot of fine lines that are all saved compared to especially poor Mary over here. I could read Mary, but I don't think I could read any of the rest of this. So I want you to compare two tombstones in the next picture. How do they differ in terms of weathering? How do they compare in appearance? And which one appears more weathered? So again, here's Mary again, and then here's that same one before from Elizabeth Potter. This one was from 1764, where Mary here was from, where is it? 1852. So these guys, this one right here is almost 100 years older than Mary, yet it's so much clearer. Rocks can weather at different rates. We call this process differential weathering. Some minerals are more stable at the Earth's surface than others. These take longer to weather. Now, calcite is very unstable at the Earth's surface and in certain climate types. Which types in particular? Well, if it rains a lot, it's going to break down. Now, this is something we need to be aware of, but it's actually a very helpful thing. The fact that calcite breaks down and goes, into a solution is the reason why you have bones. Your bones contain a tremendous amount of calcium in them. Your whole body contains a lot of calcium. And the only way you're going to get that is from things that are made up of calcite breaking down and getting into the water. What weathering process causes these tombstones to dissolve? Is this a chemical or a physical reaction? Chemical or physical? You got 10 seconds. All right, so let's take a look at this. Which weathering process causes the tombstones to dissolve? It's chemical, acidification. But even slate tombstones are not immune to weathering. So what process is happening here? Is it physical or chemical? So our buddy Reverend Ebenezer Prime, his tombstone's definitely showing signs of wear. Maybe not, like as far as rounding off edges, but you can see this red stuff running down. That's oxidation. There's iron oxide trapped somewhere in that slate. It's breaking down, it's rusting chemically. More tombstones undergoing weathering. What process might be happening here, knowing the climate on Long Island? So here we have frost action. Water gets in the cracks, freezes, busts those layers apart. Another tombstone weathering for almost 200 years here. This distinct color indicates one weathering process going on. Which one? Well, if it's red tinged, you're going to know that it's got to be oxidation. What other processes are occurring? You see how those layers are peeling off? Call that exfoliation. You can even see the slaty cleavage from the slate itself. So why does the climate of Long Island contribute to exfoliation and frost action? Well, where we live, temperature goes below 32 at night in the wintertime, but in the daytime it goes above 32. That process of alternating between hot, cold, hot, well, not hot, but freeze, thaw, back and forth, causes potholes in the street, but it also causes these tombstones to break. There's also living organisms that can break down rock. So these little guys are known as lichen. Lichen, small, simple, single usually, and multicelled organisms that can live on bare rock. They spray out an acid, they dissolve the rock, and then they eat the minerals that they pull out of the rocks that way. So quick review. What types of weathering processes can you see here? We've got exfoliation, acidification, and then the whole thing is red and rusted, oxidation. In fact, the tombstones themselves tend to fall over or get picked up out of the ground by the freezing water in between the soil particles. So every winter, the ground freezes, thaws, and particles move around, and then those tombstones stop being straight and they fall over. It's time for us to leave, but the weathering process continues 24/7. What do you think this place will look like in another 50 years?